Hi, this is Mark Struthers. Today we're going to be talking about 2D and 3D medical imaging. Traditionally, medical imaging was X-ray and two-dimensional. In a 2D X-ray, all physiological properties and tissue densities are superimposed to create a snapshot of the patient's anatomy and physiology at a specific time. Musculoskeletal anatomy is inherently 3D, and an accurate assessment of the patient's anatomy is therefore largely dependent upon the individual viewer's experience and the ability to assess 3D anatomy by analysis of 2D images only. Prior to looking at 3D reconstructions and 3D viewing of images, let's take a look at the differences between two-dimensional versus three-dimensional images. A two-dimensional image represents an object with just two dimensions, for example, length and height, while a three-dimensional image has three dimensions, length, width, and height. When assessing three-dimensional imaging, we need to understand that we have two eyes, and each eye receives a different image due to their slightly different positions in the head. These differences are referred to as binocular disparities, and these disparities are processed in the cortex in the brain to give us depth perception. Due to the front-facing location of our two eyes, each eye sees a very similar yet slightly offset image when looking at an object in space. The brain can then interpret this offset as a binocular depth cue. While binocular disparities are naturally present when viewing a real three-dimensional scene with two eyes, they can also be simulated by artificially presenting two different images separately to each eye using a method called stereoscopy. Stereoscopy or stereo views are 2D images taken at different angles that are used to create a three-dimensional image of an object. The left image is presented to the left eye, and the right image is presented to the right eye. When viewed together, they give us a three-dimensional image. We no longer use different angles when acquiring X-ray images to present a stereoscopic vision to the radiologist. Today, this is accomplished through algorithms and computerization of data. This graphic is a good demonstration of how stereoscopic vision is used and how it was used in medical imaging for stereoscopic X-rays in the past. Here we see a facial bone X-ray that was done with stereoscopic reconstruction many years ago. In today's medical imaging, we use data and we map the data to create 3D images through computer algorithms. The modality and the data acquisition methods used in medical imaging play an important role in image formation. Digital medical imaging is a two-part process. The first is the collection of data concerning the interaction of some form of energy with tissue. And the second is the transformation of the data created from that interaction into an image using specific computational tools. Let's look at this process with X-ray acquisition. Here we can see X-ray is being absorbed by the tissue, and it's changing the energy through absorption. The remnant energy, or the energy that comes out of that interaction, is recorded, and this creates the data that we use to make our image. In digital imaging, a receptor records the intensity differences. These are continuous in nature and need to be changed into a number. This is called analog to digital conversion. This is what we utilize to create the data to create the images using computer algorithms. It is very easy to change the data being displayed utilizing digital imaging. So a digital image is not an exact snapshot of reality. The data remains the same, but it can be manipulated to create different types of displays. The viewer can look at specific areas or change the density and contrast as needed. Now let's get back to the difference between a 2D image and a 3D image. A 2D image only shows us the height and width. A 3D image allows us to incorporate the depth. So we're looking at data in 3 dimensions instead of 2. So we're recording all of the data in the axial, sagittal, and coronal plane of the patient, and not just 2-dimensional information. Today we can record the world in 3D using a simple computer trick. We no longer have to manipulate machinery and use multiple images, as we did in the olden days of stereoscopic X-ray. To maximize the use of the imaging algorithms, the first question when getting a 3D reconstruction is, what do you wish to demonstrate? The modality used and the area of interest that is captured is crucial in creating 3D images or anatomical 3D models. Using computers to create 3D images, we're again collecting all the data in the axial, sagittal, and coronal planes. The internal densities differ from the structural outline of bone and soft tissue densities, which are normally represented on a 2D radiograph. Computer image reconstruction uses image segmentation. This is a process by which a digital image is partitioned into various subgroups of pixels called image objects. This reduces the complexity of the image and thus allows the analysis and reconstruction to be simpler. We use various image segmentation algorithms to split and group a certain set of pixels together from the image. By doing so, we are assigning labels to pixels, and the pixels with the same label fall under a category where they have something in common. Using these labels, we can specify boundaries and draw lines and separate the information required to create the image from the information that is not so important in creating the image. Image segmentation is the process of partitioning a digital image into multiple image segments, also known as regions or image objects. The goal of segmentation is to simplify and/or change the representation of an image into something that is more meaningful and easier to analyze. The computer must be able to use the data collected to establish borders of the collimated area of interest, and then define the anatomic region of interest, which requires a histogram of the analysis of the atomic region and the intensities recorded. Pixel is a contraction for picture element, whereas voxel is the volume of the pixel or picture elements. So a pixel is for 2D representations, and the voxel is used to create 3D representations. This graphic demonstrates accurately how we utilize the pixel and the voxel in gathering the information that we need to create images. Intensity-based 2D and 3D registration of the data collected in an image exposure allows us to create 2D and 3D images. A histogram is nothing more than a graph or a map of this data. Using the data that we have gathered on a three-dimensional histogram, we're able to create 3D objects or images. With a histogram that is only a bar graph of height and width, we're only able to create a 2D image. Obviously, the images that are created today using computers are much more sophisticated than the simple images that we used in the olden days by using stereoscopic imaging technique with X-ray. Talking about 3D, stereoscopy, and 3D reconstruction in medical imaging.